In this video, we'll look at equations reducible to quadratic and solve some other applications involving quadratic equations. Here we have some examples of equations that originally are not quadratic, but we can reduce them to quadratic. For example, in this case, we have a term with m to the 4 and a term with m squared and a free term. Notice that if we replace m squared by, for example, x, then m to the 4 in terms of x would be actually called x squared, isn't it? So we can see this equation as 6x squared minus 19x plus 15 equals 0. And then we know how to solve such equation. We could either try factoring or quadratic formula. Let's see if factoring is a possibility. To check this, let's multiply the outside coefficients. So the master product is 6 times 15, which is 90, and the middle sum is negative 19. So do we have two numbers that multiply to 90 and add up to negative 19? Yes, we have negative 10 and negative 9. Therefore, we know that the left-hand side trinomial can be factored. We could apply decomposition method. If we split the middle term into negative 10x and negative 9x, copy the rest as it is, so 6x squared in front, and then group those terms 2 by 2, we can pull the common factor from the first two terms, which is 2x, leaving in a bracket 3x minus 5, and from the last two terms let's pull negative 3, and then in the bracket we have 3x minus 5 again. Okay, so yes, we can factor. The factored form is 2x minus 3 times 3x minus 5 equals 0. So from this factored form using zero product property, we know that the solution to this equation is x equals 3/2 from the first bracket or x equals 5/3 from the second bracket. However, our original equation calls for finding m. So let's use back our substitution that x is equal m squared. Therefore, we have to solve equation m squared equals 3/2 or m squared equals 5/3. And now we need to undo this square, so let's place square root on both sides of the equation in both cases. That gives us from the first equation m equals plus or minus root 3 over root 2. Remember, we always try to get rid of irrationality from denominator, so we could change this form by multiplying the top and the bottom by root 2. So that becomes plus or minus root 6 over 2. Okay, we've got already two roots, but there are two more roots coming from the second equation. So we can say or, and then m equals plus or minus root 5 over root 3. Again, multiplying the top and the bottom by root 3, we obtain plus or minus root 15 over 3. So those are the four solutions to the original equation. Notice that our original equation is a fourth degree polynomial, and we obtained four solutions. This is to expect. Generally, if we deal with nth degree polynomial equation, we should expect up to n roots. Let's see the second example. This time, we don't even have a polynomial, but notice that if we rename this x to the negative 1 by some other letter, let's call it a. We could even write it on the side, so we remember that a is the same as x to the negative 1, which is the same as 1 over x, right? So that's our substitution that we can make. Therefore, x to the negative 2 is the same as a squared, isn't it? Because a squared is 1 over x squared. So the variable expression in the first term corresponds to a squared. By renaming those expressions, we bring the original equation to the quadratic one, 3a squared minus a and minus 14 equals 0. Now we can choose to solve this equation either by factoring or by using quadratic formula. Well, in order to know if factoring is applicable here, let's calculate the discriminant. B squared, which is 1, minus 4 times 3 times negative 14. Since 12 times 14 is 168, and these two signs make it plus 1, so that's 169. This is a perfect square number, so yes, we could factor. Let's try to factor then. We'll prepare two brackets, equals 0, and since the first term is 3a squared, we have to have 3a here and a there. Then the free term is negative, therefore we have two different signs. We don't know which one is which yet. However, the product of the last two numbers is 14, and the middle term is negative 1. So we need to distribute the factors of 14 between these two places in such a way that this product and that product together gives us negative 1. That means they really differ by 1. So 3 times 2 would be 6, and 6 differs from 7 by 1. So let's place 7 here and 2 there. That works because here we have 7a, over there we have 6a. Since we want the overall sum to be negative, this 7 must be with negative sign. So negative 7 and plus 2 would work. Okay, therefore a from the first bracket would be 7/3, or from the second bracket, negative 2. Now let's go back to our substitution. We are really after x. So our a is 1 over x, which is 7/3. We need to solve it for x. In order to bring the x to the numerator, we can just take reciprocal on both sides of this equation. So x would be equal 3/7, or 1 over x is equal to negative 2 over 1, right? So x by itself would be equal negative 1/2. This time we have exactly two solutions of the original equation. And a couple more equations to try. I would encourage you to try it on your own first, but please use the method of reducing the given equation to a simpler quadratic equation. For example, in this case, I would replace the whole bracket by a new variable. Let's call it a. So we can write on the side a is the same as x minus 4. Therefore, a squared is the same as x minus 4 squared. Okay, so the first term is really a squared. The second term is a, and then it's negative 20 equals 0. Oh, this trinomial is quite easy to factor. We don't have to worry too much here. A, the product 20, and the difference 1. So 5 and 4 should work. Since the difference is positive, 5 must be positive and the 4 negative. Therefore, our solutions in terms of a are negative 5 from the first bracket or 4 from the second bracket. However, we need to remember to come back to the substitution because we are obligated to solve for x, not for a. So let's replace a back to the x minus 4. That equals to negative 5, or x minus 4 equals to 4. And then it's easy to solve for x. X would be negative 5 plus 4, so it's negative 1, or x equals 4 plus this 4 is 8. So we have two solutions in this case. Obviously, the other way of solving this particular equation would be to unfold this perfect square, combine like terms, and then factor it again. However, the method of renaming a variable expression to reduce to a simpler quadratic equation is really more elegant and quite often easier. In the last example, we deal with a rational equation. Let's multiply the whole equation by the least common denominator, which is 3x minus 1 squared, just because we want to get rid of those unpleasant denominators, right? So when we multiply by it, we have 2 bracket 3x minus 1 squared, and then plus 5 times a single bracket, because one of those brackets will be reduced, so 5 times 3x minus 1, and then equals to -2, or let's bring it to the other side, it becomes +2 equals 0. And then we see that this equation is nearly the same as the equation in example C. So again, let A represents this whole bracket. Therefore, the first term is really 2a squared, and then plus 5a plus 2. That's how we can reduce the originally quite difficult equation to a quadratic equation that we know how to solve. So let's solve for a. Can we solve it by factoring? Well, the product is 4 and the sum is 5. So yes, we can. Let's prepare two brackets. We must use 2a and a for sure. And then for the last terms, we don't have many choices. It must be 2 and 1 or 1 and 2. Since the middle term is 5, which means the inner product plus the outer product gives us 5, let's place the 2 here and the 1 there. That way we have 1a and then 4a altogether is 5a's with both pluses inside the bracket. Okay, therefore our a from the first bracket is -1/2, or from the second bracket is equal -2. And to give the answer in terms of x, let's go back to the substitution. We have 3x minus 1 equals -1/2, or 3x minus 1 equals -2. Both linear equations easy to solve. Therefore, we have 3x equals -1/2 plus 1 is 1/2, meaning x by itself is 1/3 goes to the denominator, 3 times 2 is 6, so 1/6. Or 3x equals -2 plus 1 is -1. Divide by 3, we have -1/3. So here are our solutions. Now let's go over some word problems. The Hudson River flows at a rate of 3 miles per hour. A patrol boat travels 60 miles upriver and returns in a total time of 9 hours. What is the speed of the boat in still water? Anytime we work with a motion problem, it's a good idea to fill the information in a table that starts with the golden rule rate times time equals distance. We have two parts of the trip, upriver and return, downriver. So the first row refers to the upriver part, and the second row will refer to the downriver part of the trip. So let's see what the question asks for. What is the speed of the boat in still water? Okay, since that's the question, let r be the speed of the boat in still water. Do we know the rate of the river? Yes, we do. The Hudson River flows at a rate 3 miles per hour. Therefore, if the river flows, for example, to the right with the speed 3 miles per hour, however, the boat flows against the current with the speed r, therefore the overall speed of the boat is r minus 3. The speed of the boat is decreased by the rate of the current. However, when the boat returns, it's going downriver. Therefore, this time the river goes in this direction and the boat itself goes in the same direction, which means that the river is pushing the boat forward, so the overall speed of the boat in the river is r plus 3. What else do we know? We know that the boat travels 60 miles before it returns. So the trip one way is 60 miles and the other way is 60 miles in a total time of 9 hours. Therefore, we don't know this time, we don't know that time, but we know the total time. Overall, the time is 9 hours. That means that we can develop expressions for these two boxes representing time spent traveling upriver and downriver by using the formula rate times time equals distance. To solve this formula for time, what we do, we divide distance by rate, isn't it? So we follow this recipe. Therefore, the expression for time upriver is this distance, 60 miles, divided by this overall rate. so it's 60 over r minus 3. While downriver is this distance over that rate, so it's 60 over r plus 3. Since we know that the total time is 9 hours, we're ready to set up equation. 60 over r minus 3 plus 60 over r plus 3 is equal to 9. Okay, so we ended up with a rational equation. To simplify this equation a bit, we could divide it by 3, so the coefficients become a little bit smaller to work with. We have 20 over r minus 3 plus 20 over r plus 3 equals 3. And now we can get rid of those denominators, multiplying the whole equation by r minus 3 and r plus 3. Okay, so the first term would be 20 times the missing bracket, which is r plus 3, and then plus 20 times the other missing bracket, which is r minus 3, equals overall 3 times the two brackets. But notice that when we multiply these two brackets, we end up with r squared minus 9, using difference of squares formula, right? Okay, so what's left to do is to release all those brackets and rewrite our equation in the standard quadratic form. So we have 20r plus 60 plus 20r minus 60 equals 3r squared minus 27. Now these two 60s are gone, and let's rewrite our equation over here, starting with 3r squared on the left. Now let's bring these two terms, which make 40r, to the right. That becomes negative 40r, and finally negative 27 equals 0. Since these numerical coefficients are pretty large, let's apply quadratic formula this time. So our r could be negative b, which is 40, plus or minus b squared, which is 1600, minus 4 times 3 times negative 27. Everything over 2 times 3, which is 6. And then using our calculator, we have 40 plus minus root of 1924, everything over 6. Since this is a word problem and 1924 is not a perfect square number, we don't need to give the exact answer, we need the approximation. So it's okay to use a calculator and approximate these roots. Using the positive sign, our root is about 13.98 rounded to 2 places, or using the negative sign, we have about negative 0.64. Obviously, we need to exclude the negative possibility because the boat is going forward, so its speed must be positive. Therefore, we can give the final answer. The speed of the boat in still water is approximately 13.98, which is nearly 14 miles per hour. And here's another word problem. It takes 4 hours for 2 carpet installers to install a carpet in a room. If each installer works alone, one of them could do the job in 1 hour less time than the other. How long will it take each carpet installer to complete the job alone? Okay, so that's a work type of problem. To organize information, we can use a table that starts with the formula rate times time equals 1 job to do. And we have 2 installers, so 2 rows, like this. First installer and the second installer. In the last row, we'll record the work together. In each case, they need to complete just 1 job. Install the carpet. So it takes 4 hours for 2 carpet installers to install a carpet. Okay, therefore the time when they work together is 4. If each installer works alone, one of them could do the job in 1 hour less time. So we're comparing times. So we are after the expressions that go in those 2 boxes. Assume that the first installer is faster. Therefore, it takes him less time. 1 hour less time than the other. So if we introduce t for the time needed for the second installer, then the t for the time needed for the first installer would be 1 hour less. Therefore, the expression is t minus 1. Okay, so let t represents time needed for the slower installer to install this carpet. Now let's look at the rate column. Rate from this formula is really 1 over time, isn't it? Okay, so the expression for rate in this box is 1 over t minus 1. In that box is 1 over t. And finally, when they work together, is 1 over 4. That's the rate of performing the job. In work type of problems, we are comparing those rates. We are adding the rate of first installer plus the rate of the second installer is the overall rate. So that's how we develop the equation. 1 over t minus 1 plus 1 over t is equal to 1 over 4. And now we need to solve this equation. So as usual, we multiply by least common denominator, which in this case is 4t times a bracket t minus 1. After multiplying, the first term becomes just 4t because the bracket will be reduced. In the second term, we reduce the t, so what's left is 4 times the bracket. And in the last term, we reduce the 4, so we have t times the bracket t minus 1. Okay, and now what's left to do is to release those brackets. We have 4t plus 4t minus 4 equals t squared minus t. Next, we need to bring everything to one side. So let's start with the right-hand side. T squared, and then we have 8t goes to the right-hand side, becomes negative 8t, and negative 1t, so it's negative 9t altogether. And finally, bring the 4 over, that becomes plus 4 equals 0. Okay, now we need to solve this equation. And this time, we definitely can't factor it. Therefore, we need to apply quadratic formula. Our t would be negative b, which is 9, plus or minus square root of b squared, which is 81, minus 4 times a, which is 1 times c, which is 4. Everything over 2 times a, so it's just 2. Okay, let's simplify this. 9 plus minus square root of 81 minus 16, that's 65. Everything over 2. So this time again we are going to approximate using a calculator. Root of 65 is tiny bit larger than 8. So let's evaluate these roots on a calculator and see if you've got the following approximations. The positive case gives us 8.53, or with the negative case we have 0.47 when rounded to 2 places. So how to make sense of these two answers? Which one is correct? Remember, the t is the time needed for the slower installer. This time will have to be larger than the overall time that is needed for both installers to do the job. Because obviously, to install the carpet by one person, it will take longer than by 2 people. Therefore, our answer must be larger than 4 hours. We have to exclude this possibility, and the final answer is approximately 8.5 hours. So let's give the answer. One installer needs 8.53 hours, and the other installer needs 1 hour less, so 7.53 hours to complete the job alone.